Right now, every major enterprise is plugging into the exact same frontier language models. The tech stack is essentially identical across the board. But assuming that identical cloud resources will automatically yield identical organizational output is a trap. The playing field is not actually level. The first misstep is treating these models like a fast typewriter. Relying on basic prompt engineering is a massive regression of the technology's potential. The second misstep is treating the AI like an indexed library, using basic retrieval augmented generation, or RAG, to pull up documents. This treats the system as a passive repository rather than an active participant. When the AI model and the data are commodities, a stalled organization indicates a flaw in how the work is being designed, rather than the tools themselves. To scale operations effectively, we have to move past simple prompting and focus on harness engineering. This means orchestrating strict processes and choreographing how multiple AI agents interact with each other. The role of the engineer is shifting. Instead of executing individual tasks in a linear sequence, the engineer is now directing a swarm of autonomous agents. Building the structures that control this swarm requires a specialized discipline known as method engineering. Method engineering focuses strictly on designing the constraints, rules, and workflows that govern the agents. You aren't designing the final product yourself, you are designing the system that produces it. Organizations reach a point where manual prompt tuning no longer adds value. At that stage, they must shift engineering resources toward the methods that govern the AI agents. The physical space where this methodology lives is the Interactive Working Environment, or IWE. It is the necessary evolution beyond the traditional interactive development environments used by coders. An IWE integrates specialized agent roles with a persistent record of the human engineer's preferences and past logic, effectively a digital twin that ensures the AI understands the engineer's specific architectural style over time. There is a widespread assumption that deploying AI in complex systems architecture will simply make the work happen faster. In reality, the engineer must read the output, verify technical accuracy, and strategically guide the logic. The total time a human spends at the keyboard remains roughly the same. While AI in an IWE handles the density of the work, the primary benefit shifts from raw speed to the rigorous quality and scale of the final system. A single engineer in a well-structured IWE can produce the strictly validated output of an entire enterprise department, all within their standard working hours. To eliminate AI hallucination, this environment relies on a rigid 5-step generation pipeline known as the First Principles Framework. Step 1 is the intake. Here, the raw objective is tightly defined. Step 2 is the audit. The AI analyzes the intake, checking modularity and ensuring alignment with state-of-the-art practices. Step 3 generates the Design Rationale Record, or DRR. This meta document explicitly states what the AI will execute, the literature it will reference, and why specific patterns were selected. Step 4 is the external review, conducted by a separate reviewer agent to maintain objectivity. This review runs in 4 passes: verifying architecture, checking content substance, confirming state-of-the-art validity, and running a semantic check for naming collisions. Finally, Step 5 pours this validated data into the monolith output. Imposing this strict orchestration of design methods is exactly what separates a highly reliable AI systems harness from an unpredictable chatbot. Controlling this pipeline requires engineers to master one critical ontological distinction. We must clearly separate work from method. Work is the actual runtime execution of a specific task. A method is the design time abstraction defining exactly how that work should be approached. Human engineers need to dedicate their cognitive bandwidth almost entirely to optimizing the method, the harness itself. Executing the actual work should now be treated as the exclusive domain of the AI agents. Confusing the method with the work causes a specific failure. Engineers attempt to micromanage the AI agents step by step, rather than engineering the overarching system. There is a practical challenge in deploying these AI-native frameworks inside highly structured legacy organizations. Most engineers lack the formal C-level authority to mandate a top-down integration. The solution is a tactic called semantic control. It allows engineers to drive architectural change from the middle out. If you try to introduce a new workflow using legacy engineering terms like components or modules, you will immediately trigger corporate friction and endless debates over existing definitions. To bypass that friction, you engineer a new, uncontested lexical space. By introducing a clean term like elements, you avoid existing biases and isolate your new methodology. In systems engineering, controlling the terminology effectively allows you to control the organizational workflow, and you can do it without ever requiring formal permission. To permanently cement these new AI methods into the enterprise, you have to execute a velocity-to-value translation. Enterprise management rarely responds to the elegance of an architectural model. They respond exclusively to financial utility. This chart shows exactly how technical velocity scales into financial impact. You have to translate a technical win, like a 1-second micro-efficiency in a process, directly into a mathematical proof of saved enterprise capital. Presenting that undeniable financial proof is what permanently secures the adoption of your AI-native method within the corporate structure. The value of the modern systems engineer is no longer measured by how quickly they draft documents or write code. Instead, it is measured entirely by their ability to architect the semantic harness that guides the intelligent swarm.